Welcome to the Crazy Hat Chemist. So today we're doing another video in bonding and molecular structure. So let's get moving. Bam! Today we're talking about hybridization. Hybridization is essentially a correction factor for the valence bond theory. So let's find out more details about it. Here we go. When atomic orbitals, that is pure s, p, d, and f, are mixed, then a set of new hybrid orbitals, that is sp, sp2, sp3, sp3d, sp3d2 are generated for bonding, such that the hybrid orbitals formed conform to the geometric shapes predicted by the valence bond theory, and these are equivalent for the bonding of those atoms geometrically in 3D. Okay, so let's take a look at how to label them. Labeling the hybridization of any atom once you've got the Lewis structure is super simple. Understanding the concept is difficult, but labeling it, piece of cake. So we got the central domain column, we got a counting column, and we got a hybridization column. So central domain 1, counting S, hybridization none. Okay, I'm assuming you know what a hybrid is. Like a hybrid car is gas powered vehicle with a battery, and that's a hybrid in between the two. Some cars are just gas, some cars are just battery. Those are not hybrids. So a hybrid car has a gas and an electric portion of it, and then they combine them together to make a hybrid. If you just have an s-type orbital, that's not a hybrid. You need at least two different types in order to have a hybrid, like a battery and an electric portion. So this central domain has two things around it now. So it's sp1, and that's called sp hybridized. Notice that it is truly hybridized here. Okay, three domains around the central element here. That's sp1, p2. So I'm just counting from the top and moving down. Okay, and that is sp2 hybridized. Four domains around the central element. That's sp1, p2, p3. That's called sp3 hybridized. Five domains around the central element. That's sp1, p2, p3, d1. And that's sp3d hybridized. We forget about the 1. Okay, and then the last one here is 6 domains around the central element. That's sp1, p2, p3, d1, d2 hybridized. That's called sp3 d2 hybridized. Okay, so getting the hybridization, once you get the Lewis dot structure, all you're doing is counting the domains around the central element. It doesn't matter if they're bonding or non-bonding domains, you are counting the domains around the central element. Those are just counting. You can count them 1 through 6, and you got the hybridization that corresponds to that. Okay, so let's try this out. That's not a hybrid, right? But we're just going to count around this central 6-domain structure. That's S. P1, that's SP, that's SP2, that's SP3 for 4 domains, right? SP3D for 5 domains, and 6 domains, SP3D2, that's 6 domains. Hopefully that's super simple there. Okay, hybridization. So hydrogen and hydrogen fluoride and fluorine can all be explained with an molecular orbital overlap. However, methane, that's CH4, and other similar molecules cannot be explained with this. Vesper predicts and experiment confirms that CH4 methane is tetrahedral in shape with bond angles between those atoms of the hydrogen molecules of hydrogen atoms of 109.5 bond angles. This means that all 4 bonded hydrogens are identical in their bonding. Okay, the electron configuration is carbon. That's a helium core, and 2s2, 2p2 has 4 valence electrons in carbon. Okay, so we're going to explain why methane and the hybridization of methane and how you get the hybridization and how the whole hybridization process is explained. Okay, if you were to do the helium core and then do an orbital box diagram thereafter, you get 2s2. You see those 2 pairs of electrons are paired, anti-parallel spin, and then there's a 2p2, and you've got 2 unpaired electrons there. The 2s orbital is spherical and can bond in any direction, right? There's no orientation to a sphere. Furthermore, both electrons are paired in the 2s orbital and are unavailable for bonding. They're already paired. Okay, the 3 2p orbitals are at right angles from each other, 90 degrees. That's XYZ planes, which does not correlate with the experimental 109.5 degree bond angles for methane that's tetrahedral. In addition, there are only 2 unpaired electrons available for bonding, and the carbon in methane bond has 4 equivalent hydrogens. So how do we explain this? What do? We have 2 paired electrons and 2 unpaired electrons, and yet there are 4 hydrogens that are going to come in with their own electron and trying to overlap orbitals. We can't do that with what we have. So we need to do some more explaining here. To correlate with the valence bond theory is the orbital hybridization process. Okay, for methane, the use of 4 atomic orbitals s, p, x, py, pz to form an intermediate or hybrid orbitals, which have an appropriate geometry to match the experimental data. The carbon forms 4 equivalent sp3 hybrid orbitals, and these hybrid orbitals are 109.5 degree bond angles. Okay, so we're going to take this structure right here that you see, that are the valence electrons, removing that helium core, which doesn't account for any bonding whatsoever. And we're going to change this. And we're going to change this so that we unpair those electrons and have 4 equivalent unpaired electrons. And so now we have sp3 hybrid orbitals with 4 unpaired electrons at bond angles of 109.5 degrees from each other. Okay, that gives a tetrahedral arrangement of electron domains. That allows you to have that central carbon core in the middle and the hydrogens that surround it, and that gives a tetrahedral shape. That is hybridization in a nutshell. You can get it really easily by labeling the hybridization. The understanding of it conceptually is very difficult. Okay, that is the next video with the Crazy Hat Chemist. And of course, carbon follows the octet rule, right? Okay, that's why I'm wearing an octopus hat today, or maybe it's an 8-legged starfish. I'm not really sure. If you like that video, give me a thumbs up, subscribe to my YouTube channel, pass on my YouTube channel to all your friends. Love you, bye.